Good morning, Woodrow Wilson Bridge.
The Woodrow Wilson Bridge spans the Potomac River on the outskirts of Washington, D.C., and connects the states of Maryland and Virginia. The bridge carries the I-95, the most heavily traveled road on the east coast of the United States. It also forms part of the congested Washington commuter beltway. The bridge was built in 1961, and its 6 lanes can no longer cope with the enormous volume of traffic. The result is gridlock. The nation's capital is grinding to a halt. It's time for a new bridge. The ambitious plan is to build a monumental 12-lane super bridge, twice as wide and 20 feet higher. It will have to open for river traffic using a bascule or drawbridge mechanism. It will be the biggest bascule bridge in the world. The new Woodrow Wilson Bridge will be the biggest bascule bridge ever constructed. It will carry 12 lanes of interstate traffic, and its 4 gigantic drawspan sections will have to open approximately 70 times a year. It's being constructed on a massive scale. It's costing $2.5 billion and is the biggest transportation project in the U.S. It has 30 separate contractors and over 1,000 workers. This colossal operation is run like a military campaign by former U.S. Army Major General Russ Furman.
It's one of those once-in-a-lifetime projects an individual like myself has the opportunity to be associated with.
Marine engineer Kevin Wickar oversees operations on the Potomac River.
We have a very tight schedule to meet to get the bridge completed, and we're currently working almost 24 hours a day. Even through this hot summer weather, we're pushing through, but it's been a struggle. It has.
The bridge site is now waiting for the arrival of the giant drawbridge sections, which are being fabricated over 700 miles away in Florida.
A structure of this size and this complexity, I'm not aware of any other bascule bridge this complex and this large in the world.
When they're completed, the huge bridge sections will have to make a perilous journey up the eastern seaboard of the United States during hurricane season.
The Tug Jaguar is outbound approaching the St. John jetties, checking on any inbound traffic around the St. John jetty area.
In a highly precarious operation, the massive cargo will then be lifted into place, supervised by veteran bridge builder Hokie Del Castello, who sees this as the final challenge of his career.
It's one for the history books. It's a monumental bridge. I mean, this is our nation's capital, and it's going to be one for the history books. I mean, there's a lot of dedication, a lot of hard work. These are the guys out here every day that are building bridges to cross our rivers and level our mountains.
But can a bascule bridge of this size and complexity be built? And how will the massive drawbridge sections be lifted into place?
You ready? Let's go.
1.5.
What? Get with him and get that cable off that bottom flange before it goes in them holes and we got problems.
For the kings of construction, building this monumental bridge is going to be the challenge of a lifetime. Work began on the new bridge in the year 2000. The first 3 years were spent constructing extensive foundations. The whole area was originally a swamp. It's unstable ground and difficult to build on. The approaches to the bridge are on tidewater flats, and the soil had to be consolidated through pile driving in order to carry the weight of the new roads and interchanges along the 7.5-mile construction corridor. When it came to laying the foundations of the bridge, the Potomac River was too shallow for the construction barges to work in, so the river had to be dredged. 500,000 cubic yards of dredge material were removed in order to create a construction channel in the river.
One of the challenges we had here at this site was access to build the bridge itself. Except for the main navigation channel, which we're crossing right about here, which is maintained at about 35-foot depth, all the area to the east was only about 2 foot. So the first thing we had to do was to dig out a construction access channel in this area The construction methods out here are all marine-based. Everything is basically barge-supported. All the cranes, the materials and supplies are all barged out and brought in, and that's how we have to work.
The bridge has also placed other serious restrictions on the engineers, both because of its difficult urban location and because of its unusual design. First of all, the bridge has to be low profile to blend in with the historic city of Alexandria, which is right next to the site. Pressure from local lobby groups has prevented the construction of a high bridge or a suspension bridge, and therefore forced the engineers into making a 12-lane superhighway, which will still have to open for river traffic.
We're in a very populated area, the city of Alexandria, or an urban area that's really challenging and tough to construct in, with a lot of human issues. The city wanted to ensure what was there was compatible with the environment that their citizens ought to live in.
The engineers are also being restricted by a variety of environmental and cultural concerns. There's a bald eagle sanctuary right next to the bridge, and a slave cemetery has been discovered on the edge of the site, which is making the contractors reroute the approach roads.
There were 1,879 graves here. In the city of Alexandria, for Black history purposes, we only have 2 landmarks. It's so important because all we have now is just 2 cemeteries, this cemetery and another one, and churches to know that we were here.
The bridge also has to fit in with the monumental architecture of Washington, D.C.
They wanted a signature-type bridge that went with the arches of the other bridges crossing the Potomac in Washington, D.C., so we have that very beautiful arch-type construction that you see out there. Very hard to construct, but aesthetically very beautiful.
The desire to create a modern version of an arch bridge is testing the limits of what can be done with concrete and steel. How is it possible to build an arch shape in modern materials? Crucial to the design is the creation of V-shaped piers, which will support the roadway and form an arch-like structure. However, unlike a conventional arch bridge, where the keystone at the top of the arch deflects all the loads, the V-piers are held together by horizontal concrete girders, which resist all the forces which are trying to split the V-pier in half. The V-piers are constructed out of hollow concrete segments, which are molded in the prefabrication yard on the Maryland shore.
What we have here is the precast segment storage area for the Maryland Approach contract. We had a total of about 650 segments to cast. The casting beds are down the end there, and every piece is somewhat unique.
Work on these massive building blocks is going on virtually round the clock. Pouring the concrete for each segment can take up to 13 hours.
The lines, the hoses that the men are putting into the form, they're vibrating the concrete into the form, forcing the concrete to the bottom of the form.
When the concrete is set, the segments are raised out of the casting bed by huge gantry cranes, which can lift 150 tons.
I'm coming down.
They're then ferried out to the construction site by barge, where they're lifted into place on the V-piers, piece by piece. The construction of the V-piers is going on day and night in up to 100-degree heat. Kevin Wickard checks on their progress.
How are they making out? Who's in there?
The V-piers are hollow to minimize weight and have access holes for maintenance.
Hey, Jose, how you doing? You get that sealed? Okay, seal it up. The segments have been put together, 10 foot at a time, erected up to this point. These cables here are temporary stays. They act to hold the V-pier from falling down until the final tie beam goes through the center.
Once the V-piers are complete, steel girders are laid on top to carry the roadway. This pair of girders is about to connect the bridge to mainland Virginia. It's a key moment for the construction team. They're about to discover if the approach road properly lines up with the giant bascule V-piers. Supervising the lift is Mike Bonin, who has been in the bridge building business for almost 30 years.
It is rather a major event, but now we get to find out whether our survey and geometry control has been tracking properly and that the approach span does indeed meet the bascule.
The huge crane that will lift the girder is brought in by barge and secured to the riverbed by a process known as spudding, in which a huge steel pin is driven through the barge into the mud. The pick points on the girders have been calculated by the engineers, but it's the crane operator who has the final say on whether the pick is safe enough. Not only is his life on the line, but also the lives of all the men who are working underneath the steel girders. Operator has to keep a close eye on the direction and strength of the wind. 100 tons of steel are dangling 70 feet in the air. Once an iron worker has grabbed the bottom corner, the girders are lowered on a diagonal so that each set of holes can be pinned and bolted one after another, like the teeth on a zip fastener.
Ricardo, when you start letting it down, just watch it on that side and it doesn't get the strain, okay?
Yeah.
Is lowered onto earthquake-proof shock absorbers so that it can withstand any future catastrophe. It's a near-perfect fit.
All right, we're down. Get it bolted up.
It's a very good fit. We're very pleased with how it went together today. They hit very close to theoretical. We've got temperature variations in the length of the girder. We'd never know exactly precisely where it's going to sit, but we're all very pleased with how well it's fit up.
Now that the bridge has been connected to Virginia, the engineers are preparing themselves for a much heavier and much riskier lift. That of the first drawbridge sections, which will soon be installed on top of the gigantic bascule V-piers. The 4 pairs of bascule leaves, which will lift for river traffic, are being constructed 700 miles away in Florida. It's mid-July, and soon it'll be hurricane season, which could jeopardize the safe delivery of the bridge sections. In the city of Palatka, the race is on to get the bridge sections finished before the weather deteriorates. The engineering involved in the drawbridge is so complex that only 2 companies felt up to the job. The winner of the contract was PDM Bridge, run by John Grabowski, who has built some of the toughest bridges in America.
One of the areas that we've specialized in is complex structures. Structures such as bascule bridges, arches, truss bridges, those types of structures, and along with that, there's a higher degree of risk in building those. When you get into complex structures, you're not always certain the challenges that you're going to be faced with because it's not as straightforward. They're not a repetitive type of a structure. In addition to that, there's the safety challenges. These are very, very, very large girders, very heavy pieces. Some of the heaviest pieces are 150 to 160 tons. So handling those pieces and fabricating those pieces have presented a whole new set of challenges for us.
In the heavy fabrication shop, 32 employees are working 2 10-hour shifts, 20 hours a day. Here the steel is cut into the intricate shapes which will make up the bascule sections for the Woodrow Wilson Bridge. This is a massive job for the company. Nothing like this has been built before, and the pressure is on to get these enormous pieces finished in time. Fab shop manager is Ben Bristol.
This is our heavy fab shop where the big action is. This is intense labor. I mean, these people are in here working through this 10 hours a day in the heat, which gets to 100 degrees each day, along with the heating and welding that goes on. One of the challenges of fabricating this type of structure is each one is unique in size, in shape, in grade. So we have to custom model each one of these pieces.
The girder joints are welded using an automated tractor device. Because of the unusual size of the welds, 8 to 10 passes are made on each joint. Torches heat the metal to 350 degrees Fahrenheit to help prevent cracking when the weld and the base metal cool. These are difficult welds and they have to be perfect. The Woodrow Wilson Bridge is a big challenge for the welding team.
I feel really good about working on the Woodrow Wilson Bridge. My father's a welder, his father's a welder. I took it all 4 years of high school. I enjoy being able to take metal and put them together and cut them apart if they need to be cut apart. I guess I just enjoy the hard work, just to let a man know that a woman still can run with him.
Once one side of the drawbridge section has been welded, the next difficult task is to flip it over to weld the other side. This girder weighs over 90 tons. 2 50-ton overhead cranes are used to roll the girder to make sure that neither one is overloaded by this massive piece of metal.
This is a very critical lift. On this project, there are 16 girders of this size. Each one of them will be rolled one time.
This is a trunnion girder, which will eventually hold the pivot around which the drawbridge will hinge.
This is the most critical part of the move. The girder is now vertical. We are using blocking to start the rolling process that will start the girder to tilt out of the vertical position. Then the center of gravity will take over and the girder will lay back over with the far side up.
Amazingly, the whole process of rolling this metal monster takes only 5 minutes. As the work continues in Florida, back in Washington, the engineers are anxious to receive the drawspan sections.
Lots of trepidation because this whole thing's been done on paper. I mean, it's been all laid out. I mean, the pieces have been constructed but never put together. So everybody hopes that that measurement is precisely right when that piece gets raised, that the holes will line up and they can put the bolts in. And we hope nobody made a mistake in the process.
To ensure that the drawspan sections will fit at the job site, they're fully assembled and checked for alignment in the heavy fab shop in Palatka, Florida. Each section weighs a massive 1,600 tons and takes 5 weeks to bolt together.
Right now we're standing inside of one half of one of the bascule bridges of the Woodrow Wilson project. The total tonnage of this structure that we're standing in here is about 1,600 tons. Right above us here is the trunnion, and this is what this leaf rotates on when it opens up. The wire that you see that's going through the trunnion is a piano wire that we use for a gauge that is checked daily to assure that we're holding all of the dimensions, vertical, horizontal, and lean within the dimensional tolerances as we continue to erect through the bridge. Inside this massive structure, we're only allowed to be 5/1000ths of an inch out of tolerance. Vertical, horizontal, and any tilt.
If the bridge builders have got these precise measurements only slightly wrong, there's a serious chance that the drawspan will not fit when it gets to Washington. The other major worry is that outside the heavy fab shop, the storm clouds are gathering and the hurricane season is only days away. Because the bascule or drawbridge sections of the new Woodrow Wilson Bridge are so huge, the V-piers which will hold them have to be extra large and have to be cast in place on the river. There is no crane big enough to assemble these giant structures from precast segments. So 40,000 cubic yards of high-strength concrete have to be poured into the superstructure of each mammoth V-pier. The concrete is piped from the Virginia shore to fill the steel structure as it climbs into the air. The concrete is poured into green reinforcing steel bars, which physically hold the concrete in place and give it additional strength and flexibility. While they're under construction, the bascule piers are supported by what is known as falsework, metal structures that hold the concrete in place until it solidifies.
On the other side of the channel is what we call the falsework, or the scaffolding for the construction of the cast-in-place piers. And it's really a significant effort due to the size of the piers, the weight of the piers, trying to produce this shape very precisely out over the water, leapfrogging the forms up for the next pour, just basically working our way up the legs.
Creating structures this complex and on this scale is pushing the limits of what can be done with concrete.
With massive structures like this, it's much harder to work with the concrete. Concrete generates an extreme amount of heat. The interior of the concrete wants to get hotter than the exterior of the concrete. So we run cold water through cooling pipes to regulate the temperature of the concrete after we cast it. And that allows us to maintain an equal temperature from the outside of the concrete to the inside. If we don't keep the concrete cool, it will develop what they call thermal cracks. Cracks that are generated just from the sheer heat. Even with our cooling pipes, the concrete will get to around 160 degrees. If we didn't have the cooling pipes in there, it would get in excess of 200 plus degrees and causes a lot of trouble.
Two of the bascule V-piers are almost complete and have some of the massive moving parts of the drawbridge already installed.
Behind me you can see some of the machinery involved in moving the bascule span, and that's really where our fixed structure meets our movable structure. Well, the bascule is basically a balanced seesaw or teeter-totter, like when you were a child on the playground. There's a motor that drives a gear that literally rotates the span about a hinge, and that allows us to move the span up and down and rotate it to allow boats to pass through the channel.
At the back of the hinge is a massive counterweight box.
Right now I'm standing on the counterweight box, which is the balance point for our draw span. These access holes that we see, one that I'm standing on, allow us access to the interior to place the steel and the concrete that act as the dead weight for our balance.
Back in Florida, the first massive bascule section is finished and will soon be ready for transportation. But in order to move it, it first has to be broken down into smaller pieces.
We've actually assembled the whole bridge just like it'll be assembled in the field. And then we take the bridge back apart and we paint it, and then we move it down to ship it. And this particular project is being shipped by barge. Because of the size of these pieces, barge is the only way that we can ship them. And there's no way that you could ship those by truck or rail.
The PDM plant at Palatka has its own dock on the St. Johns River. Here on a 1,000-ton barge, the end tow sections of the first two bascule leaves are being reassembled for shipping. A team of specialist ironworkers has been brought in for this high-precision job. The team is led by Vern Nix, who has been hanging steel for 40 years.
We basically do bridge erection all over Florida, North Carolina, and Georgia, and we hang a lot of steel that PDM fabricates. It's a very hazardous trade. It's pretty risky. You're working high up. Well, you're always dealing with a lot of weight, and so you always have fall hazards and pinch hazards where if you get in the wrong place in the wrong time, you could lose an arm or a finger or a leg, and everything's heavy and it's hot.
Vern's team needs to align the structure to within 1/16 of an inch of its original design.
When they fabricate this in the shop, it's in a controlled climate condition, and when you come out here, it's in the hot sun, and we're on a barge that's kind of floating around. From the last survey results, it shows that we need to move this girder 1/4 inch this way, and the other girder on the far end has to go 1/4 inch in the opposite direction.
Vern's team uses 100-ton jacks to raise and move the girders. By the use of a simple hydraulic hand pump, this massive girder can be realigned with incredible accuracy.
This is another 100-ton jack, and what we've got is another set of jacks down there that's holding this end from moving, and we're going to move this end first. By applying pressure here and releasing that pressure, this whole beam should move back that direction. So Pepe, go ahead and start pumping it up. And what we're going to do is we'll build up some pressure. You can't really hardly see it move, it's just in very small increments. Okay, now that he's built up pressure down there on that jack, Robert's going to hold 2 1/8-inch shims in place here, and we're going to push the beam back till it's tight, and in effect what we've done is we've moved the beam back 1/4 inch. Raphael, bleed the pressure off of that pump.
It's a critical operation, and there's no margin for error. If Vern gets the alignment wrong, it will have a knock-on effect throughout the whole structure, and the bascule sections won't fit when they're lifted into place in Washington.
All right, Pepe, start pumping down there, okay? A little more. Pepe, just a little bit more. All right, hold that right there. Okay, looks good. That's move this beam back 1/4 inch, and now what we're going to go do is on the other end, we've got to move that other beam 1/4 inch that way. And in effect, we've moved the bridge. So then we resurvey, and hopefully it's in the right place.
Back in Washington, time is moving on, and the engineers are anxious to receive the delivery of the barge.
From the date this contract was let, it's probably a month or so behind. The delivery of the barge has a large impact on us in that we've reached a critical stage where that piece has to be here before work can really progress well on the project. So there's a lot of surveying being done down in Florida and alignment of the girders, and also you're now paying attention to the weather. Last thing we want is to put a barge on the water and have a problem at sea.
The shipping of these unique structures is not straightforward. There are major risks involved, and the best route up to Washington is still to be decided. There are two options. One is up the St. Johns River through the city of Jacksonville. Here the barge will pass under an old-fashioned railway bascule bridge, constructed in 1922. From there it can either travel via the Intercoastal Waterway, a protected channel which runs up the eastern seaboard of the United States. Or the other option is that after Jacksonville, it can go blue water into the Atlantic Ocean. If the barge goes intercoastal waterway, it will have to be pushed by a high tugboat. If it goes into the ocean, it will be pulled behind a powerful, low-bodied tug. The man who has to make that decision is John Hall of the tugboat and barge leasing company, Woodrow Marine.
The disadvantage of the inside boat is visibility. The loads are quite high on the barges going to Washington, and it makes it difficult to line yourself up with the bridges, and you're more apt to have an accident by either striking a marker buoy or a bridge. There are no marker buoys or bridges in the ocean, so therefore it takes a lot of the danger out of the equation. The risk is that the ocean is unpredictable. It could get rough enough to dislodge it or even jettison it overboard.
The bascule sections have been tied down by naval architect Bill Stewart. Ballast holes will be filled with seawater to stabilize the barge. The calculations for the tie-down have been made on the assumption that the journey will be up the intercoastal waterway where the precarious load will be more protected from the elements.
The load is very, very concentrated on this barge. It's going in through 8 major points on the deck, and this is way in excess of what the barge has been designed for.
Because the barge is carrying such an unusual structure, the tugboat company is concerned and thinks it's better to take the barge into the ocean. To go safely up the intercoastal waterway would require additional tugboats to help with visibility and steering. This would cost an extra $100,000. Jerry Martin has to meet the delivery deadline at all costs, but John Hall favors the ocean route.
The barge, I went down and looked at it the other day, and I measured the vertical limits on it at 29 feet, and the tugboat can't see over that. And so I told them the best thing to do would be to revise the tie-down plan and let us put a tugboat on it to pull it up there.
Redoing the tie-down for the ocean will mean further delays, and the clock is ticking. Florida's hurricane season is about to start, and any further delays could have serious financial consequences. The decision is finally made to go via the ocean route, in the hope that they can outrun the weather and get to Washington by the August 8th deadline. But when the barge eventually set sail on August 2nd, the weather has taken a turn for the worse. The hurricane season has come early, and it will prove to be the most devastating one in living memory. As the first tropical storms move in, the load becomes a big lightning conductor on the St. Johns River. The safety of the bridge sections is now the main concern. The barge is pushed upstream to Woodrow Marine, from where an ocean-going tug will take over. At the bridge site in Washington, preparations are being made for the heavy lift. Hydraulic strand jacks have been mounted over the bascule girders, ready to pull the 470-ton tow sections 100 feet into the air.
They've been going through all types of scenarios here just to make sure that they're ready. So when that barge comes up the Potomac here in about 5 days or so, they're ready to go to work, and they're excited about it.
The barge is making its way toward the Atlantic Ocean, pulled by the tugboat Jaguar.
The tug Jaguar is outbound approaching the St. John jetties, checking on any inbound traffic around the St. John jetty area. Outbound for sea, be standing by on channel 13 and 16. The tug Jaguar is clear. Tug Jaguar is clear, standing by.
Captain Eddie Ellis has sailed tugboats all over the world.
This is a deep water boat. We've made trips to Japan with this vessel, trip to Italy, trip to Africa with it. We don't think we need to push it to be there on time. We feel sure we can without pushing the limits. We do not want to do that with cargo of this magnitude. We don't put it in any kind of danger. But that's the main issue here, is the cargo. Without the cargo, the job isn't any good.
A chance of showers of thunderstorms. Thursday, southwest winds 10 knots.
As the barge heads out to face the open water, back in Washington, a worrying problem has emerged concerning some of the welds on the bascule girders. Jim Ruddle, the construction manager for the whole project, has just returned from a crisis meeting.
We just had a crisis meeting on the issue of welds for the girders. We were proceeding with machining the end of the inner loop girder, and the way the milling machine passed across the steel and the way the light condition hit the steel, it gave our shop inspector just a question. And it didn't quite look right. So he investigated it by etching the weld and putting in some revealer, and sure enough, it identified the minute crack at the end of that weld.
When the bridge is finished, these girders will be constantly vibrating because of the traffic. Any defect in the welds could prove disastrous. 5 days later, the barge arrives safely from the ocean and makes its way up the Potomac River. Captain Eddie has managed to outrun the hurricanes and has succeeded in delivering the bascule sections to the job site a day early. The heavy lift of the new bascule sections for the Woodrow Wilson Bridge has been delayed because of concerns about some of the welds on the structure. After 4 days of investigations, the engineers decide that the cracking in the welds is only superficial and easy to rectify. The lift has to take place early in the morning when the tide on the Potomac River is neither rising nor falling. In charge of the lift is legendary bridge builder Hokie del Costello. It's a big day for him because this will be his last bridge. Hokie's team of 22 ironworkers arrives at 6:30 a.m. to prepare for the lift. It's a symbolic moment.
It's a critical lift. It's a 470-ton lift. People today, they drive across the bridge and think nothing of it. And there's a lot of dedication, a lot of hard work. They give a lot of things up, even sometimes their family life. These are the guys out here every day that are building bridges to cross our rivers and level our mountains. I'm getting to the age now, I want to enjoy my grandchildren a little bit. It's my swan song.
All right, Hokie, you ready on this north side? Coming up.
The first job is to take up the slack on all 4 strand jacks and check there's equal tension in each one. Once this has been done, Hokie is ready to start the lift.
All right, Hokie, I'm ready.
Al Hoffman operates the hydraulic pumps.
Coming up. Ready? Let's go.
It's a tense moment. Nothing must go wrong. 470 tons of steel, the culmination of years of work, are about to be lifted into the air. The 4 hydraulic strand jacks raise the load 18 inches at a time. A steel cylinder or ram pulls up the metal strands in 18-inch strokes. The strands are then locked in place by internal wedges, and the cylinder is retracted, ready for the next stroke. After every stroke, it's crucial that the pressures on the jacks are checked. Each corner of the load has to be supported equally to make sure that the load doesn't get dangerously off balance.
I want an elevation reading and a pressure reading from both of you.
Nick Greco is responsible for making sure that the jacks are working in unison.
Perfect, perfect. Right now I'm just monitoring the pressure differences between the jacks. We're maintaining a 2,000 PSI pressure at each jack, which equates to a 500-ton load. Also, we're monitoring the elevation difference. That way this doesn't get out of whack and cause a twist within the assembly.
Once the bascule sections have been lifted free of the barge is taken away to be returned to Florida. With the load hanging over the channel, it's a dramatic sight for the team.
That is cool. This is awesome.
Now that the barge has been removed, Hokie comes up top to manage the lift.
Nick! Ready? Let's go.
Coming up. We're coming up. Looking good. Everybody's level at 62.5. They're about 2 inches behind. We're going to level it out on the next stroke. 500 tons.
Everything seems to be going according to plan, but as the spent cable is fed through the jack, it starts to dangle freely, posing a serious hazard.
What? Shoot! Get with him and get that cable off that bottom flange before it goes in them holes and we got problems. Watch your fingers, Andy. You got to get a rope down here and pull it back or whatever. Get that rope off that bottom flange.
The U.S. Coast Guard has sent a gunboat to protect the channel during the lift.
Hey, Al!
But one boat has got through. It's a moment of light relief for the bridge builders.
They're ahead by 2 inches here.
At midday, the bascule leaves reach the bottom of the girders.
We almost got a bridge.
This is the most critical point of the lift.
Another 18 inches to go. It's going to get tighter.
For the final stages of the lift, Hokie decides to use only 3-inch strokes. He doesn't want to overshoot.
Do it in 3-inch stages. Go up 3 inches at a time, and let's watch the gauges. Watch the gauges.
The lift happens in smaller and smaller increments.
What do you got?
It's almost level.
All right. Al, let's come up on this one 2 inches.
Watch that pressure. Pressure! Pressure! We're still 1.5 inches below.
1.5. All
right, coming up.
1 inch. Both of them. How much you got to come up? How much more do I need to come up before you put that in? Andy, are you level though? Yeah.
Almost there.
So we got to come up like about 3/8 of an inch. Whitey, is it even? Just leave it the way it is.
After 6 hours, it's finally there.
That's good, thank you. Good work, guys, really. Good job. Hey, good job, guys, really.
It is a bridge now. It's an American bridge.
Sure took a long time, but we got it licked now. It's been challenging, very challenging. You know, the guys that's working on it will be very proud of it. I mean, it's one for the history book.
Very proud moment, a landmark for all of the construction workers, and 20 years from now, tell their kids I was part of it. I mean, that's what it's all about.
Well, I hope they look at it that some kind of a monument to Washington, D.C. I mean, it's going to be a nice-looking bridge.
For the kings of construction, it's a triumphant achievement.